I hope you all enjoyed hearing Richard Taylor on Friday and Peter on Monday. So those two lectures conclude our treatment of groups for this semester. And now we're going to go on to the second topic. While we've done groups, we've also done vector spaces. So this could be our third topic, rings. So rings are, we've seen examples of them, like the integers, z mod n. So examples. Z mod nz. The complex numbers, any field. So there are structures in mathematics which are sets, which are abelian groups under an addition operation with an origin, with an identity element denoted 0. And there are first abelian groups, and then they have a multiplication, which is denoted times, which is associative, and it has an identity element equal to 1. But it need not be, another example of ring is n by n matrices over a field F. So the abelian group under addition, that we understand. The multiplication, there should be a product law, A times B. It should be associative. When you multiply three things, it shouldn't depend on the order in which you multiply them. If you multiply anything by 1, you get back itself. But you needn't have multiplicative inverses. So not necessarily inverses or commutative. You get inverses in a field for everything other than 0. Here you only have inverses for plus or minus 1 under multiplication. There's no inverse for 2 or for 3 because you'd need things like a half or a third that are not in the set. And here you get inverses for invertible matrices, but here's a non-commutative ring where the multiplication law, A times B, is not the same necessarily as B times A. So rings are very general objects which have the abelian group structure under addition, like a vector space does. But instead of assuming additionally that you have a scalar multiplication, here you have a multiplication of two objects in the ring. You know, A times B is another element in our ring. So usually rings are denoted R. So we've seen examples of them, and now we want to try to develop some general theory of them, analogous to the way we did for groups. So you could imagine what a subring of a ring is. Would be a subset containing the key elements 0 and 1, closed under addition, and should form a subgroup, and it should be closed under multiplication. That's it. That turns out not to be a very useful notion, a subring. That turns out to be the wrong notion. That's the notion like a subgroup for groups. And what we're going to want to know is what the notion is of a normal subgroup. What's a kernel? So that's going to be a little bit better than a subring. So examples, so we could look at subrings of C. Of the complex numbers. That's how rings first came about. People started looking at subrings of the complex numbers. So example would be the reals. That's closed under addition and multiplication. Or the rational numbers. That's closed under addition and multiplication. Or the integers. So all of our friends are perfectly good subrings. And Gauss discovered another very interesting subring. So this is all the things of the form A plus BI, where A and B are real numbers, right? That's how you think of the complex plane. So Gauss said, why not consider the following ring, Z plus ZI? So all the things of the form A plus BI, where A and B are integers. Those are called the Gaussian integers. And you see, if you add two of these things, you just add the a's and b's so that when you add integers, you stay an integer. And when you multiply a plus bi times c plus di in the complex numbers, you get ac minus bd plus ad plus bc times I. And if a, b, c, and d are all integers, so is this an integer, and so is this an integer. So it's stable under multiplication. So this is a very interesting ring, which we're going to investigate later. It has a lot of structure similar to the integers. That's what Gauss was able to show, and that somehow initiated the subject of ring theory. I should say that there's one relation between addition and multiplication which one has to assume, namely the distributive law. Namely, if I multiply a times b plus c, that's ab plus ac. It's the sum of the product. So if it says that you get the same answer whether you add first and then multiply, or multiply first and then add. And then you also have to do this in the opposite direction, because you're not assuming the ring is necessarily commutative. This should be the same as BA plus CA. So you have to assume two different distributive laws. Now, almost everything we're going to do after this lecture, almost everything we're going to do is going to be on the subject of commutative rings. It turns out there's a lot more structure to commutative rings than there is to non-commutative rings. So that we would accept all of these things, which are commutative rings, because it doesn't make any difference in what order you do the operation, but it would eliminate this one. However, for this lecture, I want to stay in the language of non-commutative rings. We'll see some other examples. How about examples of a ring that isn't a subring of the complex numbers? Well, we could do the following. We could take polynomials over the complex numbers. So we could let R be all polynomials in one variable, x over c. So those consist of all things of the form an x to the n plus a1x plus a0, such that ai are complex numbers, and we don't bound the degree of the polynomial. Now, we know how to add polynomials. You add the coefficients. We know how to multiply polynomials. That increases the degree. And one checks pretty easily that those satisfy the axioms of a ring. And this ring would be denoted Cx, polynomials in x. You could do that or more generally, if R is a commutative ring, so is R of x. So our polynomials over R, where now you just take formal expressions of this form, where the AIs now are in R, are elements in R, and you multiply them by the usual laws of multiplication of polynomials, and you'll see that that involves multiplication and addition of coefficients. And so, for example, if we had polynomials over, let's take R is equal to z mod 2, and we wanted to multiply the polynomial x plus 1 by, say, the polynomial x plus 1, we'd get x squared plus 2x plus 1, as we would in z, but that would be the same as the polynomial x squared plus 1, because 2 is 0 in that ring. So you do multiplication just as you do normal multiplication. You gather coefficients. So this is a general way of starting with a ring and generating bigger rings. So in particular, we could do polynomials over this ring, polynomials in y whose coefficients were polynomials in x. That would be polynomials in two variables. So c x y is sometimes denoted like this, because it doesn't really make any difference what you did first, and this is polynomials in two variables, x and y. And then we could do 3 variables and 4 variables, each time adding a new variable, right? So if you think of a polynomial in 2 variables, x and y, you can think of that as a polynomial in y whose coefficients are polynomials in x, by gathering up the terms with the same degree in y. So these rings like the integers and the Gaussian integers and their relatives, were the rings that eventually formed the subject called number theory. And the rings of this nature, polynomial rings in one and several variables, form the subject that's now called algebraic geometry. And somehow the point of ring theory, which was developed at the end of the 19th century, was to realize what techniques were used in both fields that could be just abstracted to be said about any ring. There's sometimes people noticed that what they had been considering in number theory in the solving of equations and Fermat's last theorem, etc., were the same issues that people were dealing with when they were studying polynomials in several variables, and that many of it could just be put in the same language where you didn't really worry whether it was z or polynomials in 7 variables, and you just called it R. So that's the origin of ring theory. All right, now I want to deal with one thing first, which is a hilarious question. How small can a ring be? How small can a ring be? Well, it's got to be an abelian group with an addition law and an identity element. So it's got to definitely have 0 in it. All right? Then it's supposed to have a multiplication law, and the identity element is 1, but we didn't say that 1 couldn't be equal to 0. 1 might be able to be equal to 0. So the smallest ring is R, the ring with 1 element. Fields have to have 2 elements because non-zero elements have to be invertible. So in a field you need a real honest-to-God invertible element 1. But in a ring you can have 1 equal to 0, and it satisfies all the, 0 plus 0 is 0, 0 times 0 is 0. It satisfies everything. There's nothing wrong with the ring with 0 in it. And it's important to realize that you can have such a ring. However, I'm going to prove a little lemma for you, which is very stupid, but we'll do it once. That if you have any ring which is not that ring, that 1 is not equal to 0 in that ring. So that all other rings, 1 is distinct from 0. If R is not the 0 ring, then 1 is not equal to 0 in R. They're different elements of the set. So this is kind of stupid. Take an element in R. And suppose that 1 were equal to 0. We're going to show that A is equal to 0. Then A is equal to 1 times A. Because 1 is a multiplicative inverse. So if you multiply 1 times anything, you get back the thing. On the other hand, if 1 is equal to 0, this is 0 times A. Okay? Now, I claim, but 0 times A is equal to 0 plus 0 times A. Because 0 is the sum of 0 in itself. It's an additive identity in the group. And by the distributive law, this is equal to 0 times A plus 0 times A. And then if you subtract 0 times A from both sides, subtract whatever the element is 0 times A in the additive group, when you subtract it from here, you get the element 0, and you're just left with 0 times A. So not only is 1 times A equal to A, 0 times A is always equal to 0 in a ring. And consequently, this thing is equal to 0 in R. So we've just shown that if 1 is equal to 0, any element in the ring is equal to the 0 element. There's a unique 0 element, so therefore the ring reduces to 1 element. So if the ring has any elements other than 0, 1 can't be equal to 0. And you can have a ring with 2 elements. This is the smallest ring. The next smallest ring is the ring Z mod 2, which has 2 elements in it. But there one is, that's a field, because 1 is invertible. And in fact, we have a ring with any number of finite number of elements, Z mod n. It's a ring with n elements. You get several rings, by the way, with, 4, there are 2 rings with 4 elements. So you can get more rings than this, but if you wanted a finite ring with n elements, here you are. Here's an example of an infinite ring. Now, the way rings really come up in math is from the theory of abelian groups. So I'll tell you that even though art doesn't. Tell you a secret. And we'll see a lot of our examples that way. In fact, everything. And that's the best way to... Artin goes through a whole section where he shows that the integers are a ring. And it's quite complicated. That's section 10.2. And it's not very helpful either. And if you really want to see why the integers form a ring and satisfy all the axioms, it's best to see it in this way. So the best way to get rings, which are called endomorphism rings, is to start with an abelian group A, with the usual addition and identity element 0. And to let R, which is called the endomorphism ring of A, be the set of all homomorphisms F from A to A. All maps from the abelian group to itself, which are group homomorphisms. Now that's a set. So to turn it into a ring, I have to tell you what the addition law is, what the identity under addition law is, what the multiplication law is, what the identity under multiplication is, etc., etc. Okay? So I'll tell you that. So the plus law, I have to tell you what F plus G is as a homomorphism from A to A. So we're going to define the structure. F plus G is the homomorphism that takes A to F of A plus G of A. And this is addition in A. And this is addition in R. So you apply F to A and you add it in the abelian group to G of A. Now that's clearly commutative because the addition law in the group is commutative. The identity element, 0, takes any element A to 0 of the abelian group A. That's a homomorphism of an abelian group. It takes every element to the 0 element. That has the property that if you add it to an arbitrary homomorphism, right, you don't change anything because you're adding F of A to 0. So you get the same homomorphism. So 0 plus F is equal to F. The minus operation, minus F of A, is minus F of A. That's kind of a funny way of writing it. Maybe I'll write it like this. Minus F of A, where this is the minus in the abelian group A. So that is the property that if you define this, it's a homomorphism. You have to check that. And that if you add this homomorphism to the homomorphism F using this, you get to the homomorphism 0. Because if you add F of A to minus F of A, you get 0 for any A. So there's the addition law in this ring. Kind of nutty, but there it is. It's just using nothing but the addition law on A. Okay, now how about the multiplication law? What's F times G of A? Well, here's where you get something interesting. We have to come up with something associative. That's always hard to do. Remember, associativity is tricky to prove. So the only thing we know are associative is composition of mappings. That's how we constructed like the symmetric group, composition of maps from a set to a set. So we'll do the same thing here. Why don't we just call this F of G of A? And now you see why you had to go from an abelian group to itself. To compose maps, you have to make sure that G of A is an element in A, so I can apply F to it. This is a new homomorphism. Note that this need not be equal to, possibly, G times F. Because there's no reason the composition in the two directions is the same. Okay? And then you have to check, oh, the identity, what's 1? 1 of A? Well, what homomorphism should we use to preserve, when we did multiplication, to preserve the map? Where should it take an element? A. It's the identity map on A. Identity homomorphism. That always exists if you map an abelian group to itself, taking every element to itself. Okay? So now notice here that you don't necessarily have an inverse. Nor, we already noticed it doesn't have to be commutative. There's no reason that composition of maps be commutative. I'll give you examples of that. But also, when will an element F here have an inverse? When will we be able to find, or when will an element G have an inverse? When will we be able to find an element F that inverts this procedure and takes G of A back to A? Yeah, exactly. So F has an inverse if and only if it is an isomorphism of groups. And for example, this thing won't have an inverse once our abelian group has more than one element in it. So this ring, by the way, this zero ring, is the endomorphism ring of the zero group. Kind of stupid, but there it is. Where could it? I mean, there's only one homomorphism from the zero group to itself. Take 0 to 0. Okay. Now let's go through the examples and see how we got our endomorphism rings. First of all, I claim, and this is the coolest construction possible, and the only way to explain to your third grader why multiplication of two negative numbers is positive. Excuse me. You don't want to prove it's negative. Okay. I erased all the examples, but I'm going to show you how you get all these from the So for example, Z is the endomorphism ring of Z under addition with 0. I claim that that's how you get the ring Z. And so just once we understand addition and subtraction of integers, then we can construct a new system of numbers, really on the same set, that includes multiplication. How do I do this? The identification of an endomorphism. So suppose I have some map from F from Z to Z, a group homomorphism. How do I identify that with an integer? How would I make the identification of the group of the ring of endomorphisms of this abelian group with an integer? Well, what determines a group homomorphism from Z to Z? F of 0 is 0, right? That we know. Yeah, F of 1 is an integer. F of 1 is equal to some integer n in Z. Determines everything. Because if I want to know what F of 2 is, that's F of 1 plus F of 1, so it's 2n. And likewise, F of an arbitrary integer, k, is k times n. So once I know what F of 1 is, I've got my homomorphism. Moreover, F of 1 can be anything I want, because this map is a homomorphism of abelian groups. So I take F and I associate to it the integer F of 1. And I claim that that gives this set a ring structure where the product of two negative numbers is a positive number. Let's see. Let's see why this is the right way to think of the integers under multiplication. Suppose I compose F with G. So suppose F of k is k times n. So F we've associated to the number n. And suppose G of k is k times m. So G is associated to the integer m. What is F times G of k? Well, G of k is km, and I have to apply F of that. F takes anything integer and it multiplies it by n. So this is k times mn. Right? So that F times G in the ring structure that I put on this, using this identification, becomes multiplication of m and n. And if you think of what it means for a group homomorphism here to be associated to a negative integer, it means it takes 1 to a negative integer. Right? So it takes all positive integers to all negative integers. If you take 2 of those things and takes all negative integers to all positive integers. So if f is associated to a negative number, it switches these two halves of the real line. Right? Likewise, if g is associated to a negative number, it switches them again. So if you compose those two things, you preserve positive and negative. That's why the product of two negative numbers is a positive number. That's the only way to do it. It's not a convention. It's because that's the structure of the ring. And the way to get the structure of the ring is to think of it as the endomorphism ring of this abelian group. Likewise, I claim Z mod n as a ring is the endomorphism ring of the abelian group, Z mod n under plus. This is very special. Very special. Usually when you get endomorphism of abelian group, you can't identify it as a set with the group. But again, it's the same reason. You identify an f with f of 1. And once I know f of 1, since this group is cyclic, generated by 1, I know everything. So this is a phenomenon for cyclic groups to give a ring structure on cyclic groups, not general, cyclic groups. And we know that the only cyclic groups, if they're finite, are Z mod n, and if they're infinite, are Z. So we're done with that. Anytime we take another abelian group, we're not going to be able to identify its endomorphisms with the elements in the group, because we're going to have to know more than f of 1. Okay? So let's take another abelian group that's a little bit more complicated than a cyclic group and see what we get. Well, our next case, suppose we took A to be Z mod P Z squared. So pairs of elements A1, A2, where the AIs are in Z mod PZ. That's an abelian group of order P squared. What's its endomorphism ring of A? This is the ring we've seen. You have to have a map. You can think of this as a column vector if it helps, that takes a pair of elements in Z mod P squared and produces another pair of elements in Z mod P squared in a way that preserves the addition in Z mod P squared. It's an endomorphism of the abelian group. What's that? You've got it, exactly. This is 2 by 2 matrices over Z mod PZ. And you apply it, if you have an element in this 2 by 2 matrices ring, which I can't use the letter A for because so if I have a matrix B, then I say B of A1, A2 is f of my element A. I apply B to this column vector. And those are the only endomorphisms of the abelian group I get. They happen to preserve scalar multiplication because scalar multiplication in this weird abelian, this weird vector space is just given by multiplication by elements of Z. So here's a non-commutative ring. It's very rare for an endomorphism ring to be commutative. There's really no reason that composition is the same in both directions. It is for these cyclic groups because it's so stupid. And more generally, if I had A, the elementary abelian group of order P to the n, then the endomorphism ring of A turns out to be n by n matrices over Z mod PZ. So that gives you quite a nice collection of non-commutative rings. Okay. So the first two sections are really just the definition of a ring, some examples of a ring. As I say, if you know the ring of integers, you know the ring of polynomials, and you know the ring of matrices, you know all the key examples of rings. Everything is a variation of those, or subrings of those, etc. Okay. Now, what I want to do is establish a little bit of the language of ring theory in this lecture. We'll come back to do it. Now, I know we've had a huge number of words and lingos and things like that, but since you've now become familiar with group theory, you're going to find some of these at least analogous to things we've done in group theory. Okay, now in group theory we had the notion of a subgroup, but that wasn't really the critical thing. The critical thing was a normal subgroup, which was a kernel of a homomorphism. So the first thing when we define a new object in mathematics, like a ring, we want to know what are the maps between those objects. In groups, they were called homomorphisms. In vector spaces, they were called linear transformations. So what should be a map, or ring homomorphism, between two rings? Well, it should preserve the structure of the ring. That's all we want it to do. It's a set mapping that preserves the structure. So it should be a map of sets. It should be a group homomorphism 4 plus. In particular, it should take 0 to 0. It should take 1 to 1 prime, and it should take the products in R to the products in R prime. That's it. So just preserving the structure of the ring. So subrings are an example of a ring homomorphism if I have one ring included in another. So if R is in R prime is a subring, the inclusion F from R into R prime is a ring homomorphism. But that's too stupid. We're going to have a lot of other ring homomorphisms, much more interesting than that. And if we wanted to figure out what a normal subgroup is as opposed to a subgroup, we might ask, what does the kernel of a ring homomorphism look like? So we define the kernel of F as the group theoretic kernel. It's all A in R such that f of A is equal to the 0 element in R prime. Okay, and the kernel has the following interesting properties. This was a huge breakthrough in mathematics when they realized that the ring homomorphisms, the kernels were a little bit more interesting than you'd expect. So the first property it's a subgroup under plus. Because the kernel of any group homomorphism is a subgroup, and whatever F is, it's a homomorphism of groups, and we're looking at its kernel in the sense of a homomorphism for groups, so it's a subgroup. Okay. Now, what people first thought would be the case is that, like a subring, it would be stable under multiplication. And it certainly is. If A and B are in R, so is A times B and B times A. Well, we're only going to, from now on in this lecture, let's just do commutative rings. And from now on, in fact, for the rest of this semester, we're going to assume our ring is commutative. Non-commutative rings is a beautiful, beautiful subject, quite closely related to groups, it turns out. So we're skipping over this large section of the book, which is called group representations. If I have any chance at the end, I'll tell you what you missed. But you can't do group representations without non-commutative rings. But we're going to skip that, and for now we're going to just concentrate on commutative rings. The reason I didn't want to assume that initially is that these endomorphism rings are very rarely commutative. Okay. So if I have two elements in R, so is A times B, because f of A times B is f of A times f of B, which is 0 times 0, which is 0. So far, so good. Yeah, so is, if A and B is in, sorry, thank you, kernel, so is A times B, kernel of F. Here's the proof. So it just looks like it's a subring, right? This would just mean a subring. It's a subgroup. It's closed under plus, contains 0, and it's closed under product. It doesn't necessarily contain 1. Okay, but what the cool thing is that there's an additional property, stronger property. If A is in the kernel of F, and B is any element of the ring, not an element in the kernel, but any element in the ring, then A times B is in the kernel of F. So it's not just stable under product. It's stable under product where you take any element in the ring and you take the product. And the proof is f of A times B is f of A times f of B, which is 0 times f of B. And we just saw in the proof where that 1 is equal to 0 business that for any element in the ring, 0 times the element is 0. And so A times B is in the kernel. Okay? So it's better than stable under plus in multiplication. It's stable under plus, and it's stable under multiplication even when you leave it. Even when you leave it. The second element can be anywhere. So those subsets, the things which are kernels of homomorphisms, are called, for historical reasons, which I'll try to explain to you as we get on in the subject, ideals. So a subset I in R, which is a subgroup under plus and is closed under by any element B in R, is called an ideal. The actual word came from the Platonic notion of ideals. And we're going to see why it was chosen as we get a little further in the subject. It's called an ideal. It came from algebraic number theory, and it was discovered by a mathematician in the middle of the 19th century called Kummer. And Kummer realized that people had been working with certain subsets of rings which were ideals. And he wanted a more general notion, which was just a subgroup closed under this. And that was such a novel notion in algebra at the time that you define something by its general properties rather than just by, this is an example of such. And so he called it an ideal because it was a generalization of what they knew. It was the idealized version of it, the Platonic ideal. So an examples. 1, any kernel of a homomorphism. 2, the 0 set is an ideal. It's the kernel of a homomorphism that takes everything in R to 0. The 0 ring. If you map everything in R to the 0 ring, that's a ring homomorphism, and its kernel is Sorry, it's the kernel of the map, from R to R, which is the identity map. Thank you. And the third example, is R. And that's the kernel of the map R. Goes by taking everything to the 0 ring. Thank you. So these are very extreme ideals. This is as small as you can get an ideal. This is as large as you can get an ideal. We're going to show, just like normal subgroups, that every ideal is the kernel of a homomorphism. Every ideal is the kernel of a homomorphism. So that this is the most general. But I'll give you another example. If you take an element A in R, and you consider everything in R that's a multiple of A, that's an ideal, and it's called the principal ideal generated by A. See, if you add 2 of these things, you get another one because of the distributive law. And if you multiply this by anything in R, you just use the associative law to recombine that as another multiple of A. So this is another example of an ideal. Okay? Now having, yeah. Pardon? Ah, good. Well, what do you think? Suppose I wanted to make a normal subgroup the kernel of a homomorphism. What would I make it as a kernel of a homomorphism to? What's the normal subgroup, the kernel of it's kernel of a natural homomorphism to what? So why don't we try to build a new ring out of an ideal called the quotient ring? So, and since you've asked me this, why am I hiding it for you? Any ideal I is the kernel of a natural ring homomorphism or to a new ring called R mod I, the quotient ring. Okay, without giving you any detail, because it takes an element A here to the coset of I, which I'm going to write additively like that because it's an abelian group. So this is just the quotient abelian group. And I just have to tell you how to multiply things in here, right, to give you the ring structure. The quotient group with multiplication law A plus I times B plus I is equal to AB plus I. Then you take the coset of A, you multiply it by the coset of B, you get the coset of A times B. Okay? What you have to check is that that's a well-defined multiplication. And when you check that that's a well-defined multiplication, you'll see that you need this property. I'm going to go over that. I'm getting a little ahead of myself, but since you asked the question and we know the answer for groups, we might as well, that's why I say all this new notation isn't so difficult, because we know how to form the quotient group. You could do that for any subgroup of R, but to get a well-defined multiplication on the quotient group, you need this extra property that the subset be closed under multiplication by any element. So if you believe this, there's your homomorphism with kernel I. So that the ideals are precisely the kernels of ring homomorphisms. Now, let's go back to this case, and let's work out the ideals of the integers. Please. Yes, very good question. There are notions, you have to be careful though. For non-commutative rings, there are notions of left ideals, then there are notions of right ideals, then there are notions of two-sided ideals, depending on which side you want to multiply and stay closed. Two-sided ideals are very good things to have. And then there are notions of simple rings, ones which have the only ideals are this and this, just like we have simple groups. So again, our terminology that we're beginning to develop from group theory, objects, homomorphisms, sub-objects, kernels, normal, simple, all goes over nicely into rings. Okay? Good. Let me just give you an important statement, fact. The only ideals I in Z have the form I equal n, the quotient ring is Z mod NZ. So the only ideals of the integers are the ones of type 4. If you have anything that's stable under multiplication by an arbitrary element in the ring, stable under addition, then it's all multiples of n. So this, in other words, you could write n times z. And a proof, let n be the smallest positive integer in I, use the Euclidean algorithm. So just as we classified well, those are the only subgroups, so they're the only possibility. Right? We classified the subgroups of Z, and they were all of this form. Now, each one of these forms is an ideal. So the only ideals are these things generated by a single element. Now I can give you the definition of the word ideal. When people started out in ring theory, and they were working in rings analogous to the integers, doing algebraic number theory, like Z plus Zi, they had the ideal, they had the idea, that the only way to get a multiplicatively closed subset like this was to take all multiples of a given element, namely just to take things of this form. And Kummer found examples, not this case, but other cases, of rings where there were more general ideals than that. There were ideals that could not be generated by a single element. And that exploded the subject. That's what we're going to study. So this is very special, it turns out. Even though the most familiar rings have this property, that every ideal is generated by one element. Okay, I want to give you one more piece of notation, and then you'll read 10.3, learn about this, and we'll come back and talk about it more on Wednesday. This is, again, in the notion of just developing language. So we now know what an ideal is. And the final piece of terminology is what a unit is. A unit is an element A in R with a multiplicative inverse. Multiplicative inverse. I.e., there exists some element B such that A times B is 1. Okay, we saw in endomorphism rings, the units were the isomorphisms. The invertible elements are the isomorphisms. The set of all units is denoted by R star. That's not closed under addition anymore, as we're going to see, but it's closed under multiplication, and it forms a group. With identity element 1. See, I've just set it up. I've just taken the subset that I find a multiplicative inverse. So it's closed under multiplication. If you can invert A and you can invert B, you can invert their product. And it forms a nice subset, which is a group. And it's frequently an interesting question. What is it's called the unit group, of course. So the additive group of a ring is often very stupid, but the unit group is very interesting. So for a field, which are examples of commutative rings, R star is everything other than the zero element. That's the definition of a field. Everything is invertible. Sometimes I put 2 crosses, sometimes I put 3. Don't ask me why. So everything in a field but the zero element is invertible. But this is very unusual. If you take Z star, you just get the group with 2 elements. There are only 2 invertible elements in the integers. If you take Z mod NZ star, is a group with phi of n elements. The Euler number of the number of things between 1 and n that are relatively prime to n. Because invertible in this ring means relatively prime to n. And this is a very interesting group whose structure was first determined by Gauss. It's not obvious what the structure of that group is. It's an abelian group because multiplication is commutative. If we can define the units in a non-commutative ring, and if we took the units in the n by n matrices over a field F, they would be the group GLN of F, the invertible matrices under multiplication. So the 2 sort of new pieces of terminology, things we really have to get into our heads about rings that we want to study are the set of the ideals of a ring. We're going to work a great deal on that, and the unit group of a ring, which can be quite sophisticated. Quite sophisticated. And I'll pick up on that on Wednesday. those of you, I think the final material on group was really quite involved and quite complicated. Those of you who had trouble with the homework, I sympathize. It's hard. The stuff on the symmetric group is hard. The stuff I was talking about the group of motions is hard. The conjugacy classes are hard. But now we're taking a step back. We're going into more introductory material. This will be a chance to get started again. If you were a little confused at the end of group, that's not going to hurt you. We're going to start all over again. And we're right now at the stage of just acquiring the basic terminology, figuring out what the key questions are. And then that'll occupy us for the rest of the term. Good? Good. Okay, see you on Friday.